In this presentation, I will tell you about a provocative point of view. Structuralism is the origin of self-supervised learning and word embeddings. So the motivation is that word embeddings have been an uptrend in NLP between 2013 and 2018, and self-supervision is a hot trend today, basically after the release of Elmo in 2018. Also BERT was released the same year. Many researchers and practitioners are oblivious of the previous work in computer science and cognitive science, and also in computational linguistics that was pre-Word2Vec. This delays progress and makes it so that researchers have to reinvent the wheel, while there's many lessons to be learned from the previous work that happened in the field. And so the goal here is to give you an overview, which is like an incomplete personal overview, but it's a useful starting point for exploration of the history and cultural background, to start building on existing knowledge and to propose a unifying interpretation of many algorithms. What I'm going to talk about is, first of all, I'm going to give you linguistic background about structuralism, and then I will talk specifically about distributional semantics, and will give an overview of some embedding methods, and finally I will talk about how this connects to self-supervision. In terms of terminology, there's a lot of possible names for the same things: word embeddings, distributional representation, distributed representations, word vectors, distributional semantic models, distributional representations, semantic vector spaces, and so on. They basically all mean the same. The main reason why there's different names for these things is that there's different literatures that led to these names. In particular, distributional semantic models comes from the computational linguistic literature, while word embeddings comes from the neural network literature. So let's get started with structuralism. What is structuralism? According to the Oxford Dictionary, it's the belief that phenomena of human life are not intelligible except through their interrelations. These relations constitute a structure, and behind local variations in the surface phenomena, there are constant laws of abstract culture. What does this mean? Let's look at an historical perspective starting from de Saussure, and we will move from there. So Ferdinand de Saussure wrote this Cours de linguistique générale in 1916. It was actually published posthumous, using the notes from his students, and similar ideas were also presented by Wilhelm von Humboldt in the early and late 19th century. One of the main things that he introduced is the difference between langue and parole, which means the difference between language as it's defined by its rules, and parole, which is the use of the language in everyday communication. Another really important distinction that he made is the distinction between sign, signifier, and signified. A sign is a word with its meaning. A signifier is the surface form of this word, so for instance how it's written or how it's pronounced. And signified is actually the referent meaning, which means the object that is referred or the idea that is referred by a signifier. And so the fact that different languages use different signifiers for the same signified means that the choice of the signifiers is basically arbitrary. And so, where does the meaning of the signs comes from? It is basically defined by their relationship and contrast with other signs. This is a super important point, and it is actually the basis for all structuralism. Meaning of signs is defined by their relationships and contrast with other signs. I put it in big and bold here because it's a really foundational concept. So, what are these relationships? He distinguished two main types of relationship. One is paradigmatic and one is syntagmatic. Paradigmatic relationships are relationships between words that can be substituted for each other in the same position within a given sentence. For instance, if I have the sentence, the man plays, I can also say the boy plays, and so because of that, man and boy are in a paradigmatic relationship. Syntagmatic relationships, on the other hand, are relationships that words have with other words that surround them. So in this case, for instance, the man plays, man as a syntagmatic relationship with both plays and the. So let's make some examples of paradigmatic relationships. So synonymy is a typical paradigmatic relationship where you have some words that basically have the same meaning and are interchangeable. You have bubbling, effervescent, and sparkling are all have the same meaning, even with slightly different connotations. Another paradigmatic relationship is antonymy, where you have hot and cold, as in I'm going to drink some hot tea or I want some cold tea. And then there's eponymy and hyperonymy, which is when words have a relationship with something that is more general than them and this is like an is-a relationship. So for instance, tiger is a feline, lion is a feline, and tiger and lion are co-hyponyms of the same hypernym. Syntagmatic relationship examples, on the other hand, are for instance collocations, where you have some words and the words that surround them. Like for instance, if you fix the word law, you can find against the law, law enforcement, become law, and the law is passed. Colligations are a kind of collocations, but they are typed by a specific part of speech of some words. So for instance, you can say that the words before time that are verbs in the past, they all have a similar colligation. So you have saved time, spent time, and wasted time. But also you can have adjectives before time that are related to sport. So for instance, you have half time, extra time, and full time. These are the basic ideas of structuralism. So what is distributionalism? Where does the term distributional semantics come from? It's basically the American branch of structuralism. It was started by Leonard Bloomfield in the 30s, but it was developed further by Zaligaris in the 50s and 60s. Same ideas emerged also in other fields, in particular in philosophy of language. Ludwig Wittgenstein, in his philosophical investigation, says that the meaning of a word is its use in the language, which, as we have seen, is really related to structuralism. And in corpus linguistics, we have, for instance, Gerard Firth in 1957, in his Papers in Linguistics, said that you shall know a word by the company it keeps. Other relevant work are the work of Willard Quine and Margaret Masterman in the 60s. So let's get into the details of distributional semantics. All the models that we're going to see are based on this distributional hypothesis that states that the degree of semantic similarity between two linguistic expressions A and B is a function of the similarity of the linguistic context in which A and B can appear. The first formulation is difficult to specifically pinpoint, can be attributed to Harris, to Charles, to Miller, to Firth, or to Wittgenstein too. This is an example that will try to convince you that that hypothesis can be true. He filled the wampanoag, passed it around, and we all drank some. What is a wampanoag? Well, wampanoag is a made-up word, doesn't mean anything, but just by the fact that it has the relationship with the word filled, and that we passed it around and that we drank some, it probably means that it's a kind of cup or something that you can drink from. Another example could be, we found a little hairy wampanoag sleeping behind a tree. In this context, we still don't know what wampanoag means, but the fact that it's little or hairy and sleeps behind a tree makes us think that it's probably a little animal. And so when we define a distributional semantic model, basically there's four pieces to a model. First, we want to represent words through vectors, recording their co-occurrence counts with context elements in the corpus. Then we could apply some reweighting scheme on this co-occurrence matrix. Third, we can apply some dimensionality reduction techniques. And finally, we can measure the geometric distance of word vectors as a proxy for semantic similarity or relatedness. Let's define all these steps, and let's start with an example. So in this case, we will define target and context, which are the two main concepts that we will use in the remaining of the presentation. In this case, the target is a specific word, and the context are nouns and verbs in the same sentence that these words co-occur with. So if we have a sentence like, the dog barked in the park, the owner of the dog put him on the leash since he barked. If we consider only the lemmas of the words, we will have counts of how much dog co-occurs with the other words. And so we will have, for the word bark, count of 2, for park, a count of 1, for leash, a count of 1, and for owner, a count of 1. And graphically, we can represent this by showing some of these other words as axes and target word dog as a vector in the space defined by the other words. If we do this for all the words, what we obtain is a matrix that has target words as rows and context words as columns, and the values are counts. Once we have this matrix, if we want to compute the similarity between these two words, we can, for instance, compute their cosine similarity. So we figure out what's the cosine between these two vectors and use it for evaluating how two words are related. Let's make a little distinction between similarity and relatedness. As Budanskin here has highlighted, those are two slightly different concepts. In particular, semantic similarity means that two words are sharing salient attributes or features. So for instance, synonyms or hypernyms or cohyponyms are semantically similar, while semantic relatedness means that words are semantically associated without being necessarily similar. And an example of that is words that have the same function, like car and drive, or meronymy relationships like car and tire, or location makes words similar like car and road, or attributes like car and fast. But the most important thing is that because the meaning of a word is defined in terms of the context, and so the properties and features of the context that it appeared in, deciding what constitutes a context is super important because it literally defines the meaning of a word. And so there's several options that we could use. For instance, we can use other words in the same document or paragraph or sentence, or we can use other words in the immediate neighbor of a word, or we can use words assigned along some dependency paths or some other linguistic patterns, or for instance, predicate argument structures or frames, or even some handcrafted features. Any process that builds a structure on sentences can be used as a source for properties and as a context, really. Let's see some examples. So for instance, if we have documents as context, we will collect document IDs and we will say that all the words that appear in those documents appear in that context. So basically, if we focus on the word sun, here we will have that sun appears 2 times in document 1. But another potential context is a wide window around a specific word. And so, for instance, in this case, all those words appear around sun. Or we can still have the wide window, but we can consider just the content words, so words that are non-stop words. And, for instance, in this case, highlighted in blue, the words that are gonna be in our context. We can also have small windows, so here I denoted with 1 the window around the word 1 and with 2 the window around the word 2. And also we could potentially add some additional information to the occurrences of the specific context words, concatenating them with their parts of speech, if they're a noun, a verb, or an adjective. We can do the same, but also filtering the context words by some syntactic relationship path. Finally, we can also add the syntactic dependencies inside the context definition itself. And so what is the effect of using different types of context? So let's look at the neighbors of the word dog in the B and C corpus. If you use a 2-word window, you obtain words that are in a more paradigmatic relationship with the word dog. So you have cat, horse, fox, pet, and so on. If you use a 30-word window, you still have paradigmatic words, but you also now start to see some more syntagmatic words, like for instance the word kennel or the word bark. If you look at the neighbors of the word touring in Wikipedia, you will find that if you use syntactic dependencies as context, you will find cohyponyms that are in a paradigmatic relationship with touring. So for instance, other scientists. While if you have a 5-word window, you will find topically related words which are in a syntagmatic relationship with Turing. For instance, non-deterministic, computability, finite state machine. Moreover, you have a choice of different weighting schemes. So far we used row counts. There's several other options. What seems to work the best empirically is positive point-wise mutual information. But there's a lot of other possibilities. The same is true for similarity measures. We've used the cosine similarity, but there's several other options. And it seems like in most cases correlation works much better than the other options according to Keeler and Clark. Usually these models are evaluated either intrinsically or extrinsically. Intrinsically means that we evaluate them for the properties of the vectors themselves. So one example is we evaluate some word pair similarities and then we compare those similarities with judgments obtained by humans, or we use the analogy task. Extrinsic evaluations happen when these vectors are used in downstream tasks, like for instance for classification or translation, and we look at the final performance of the task. Is there a best parameter configuration? Like which context, which similarity measure, which weighting scheme? No, it really depends on the task. So now that we have an overview of what distributional semantics is, let's look at some methods. As you can see from this slide, this is just, again, a non-comprehensive list, and word2vec can be seen as distributional semantic method, but is in the top right of the third column. It means that before that, there were many other methods dating back all the way to the 50s and the 70s. So there's a really rich history. And one crucial differentiation between methods is that those methods can be either explicit or implicit. With explicit, I mean that the vectors that are learned are big and sparse, and in most cases also interpretable, while implicit methods learn small, dense vectors with some latent dimensions. And another crucial differentiation is count versus prediction, which is how do you obtain the representation itself. If you count the co-occurrences, or if you want to predict what the co-occurrence will be, and the values of your vectors will be the best values for obtaining this prediction. And this is a distinction that was proposed by Alessandro Lenci in Distributional Models of Word Meaning. Let's look at one example model. So you have this hyperspace analog to language, HAL, where you have a target which is a specific word, and the context is a window of 10 words around it. The weighting scheme is 10 minus the distance from the target for each occurrence of the word, and the similarity is Euclidean distance. If you look at the right, we have the sentence, the dog barked at the cat, and for instance the weight for dog and barked is 10 because there's no gap, and the weight of dog and cat is 7 because there's a 3-word gap. The matrix that we obtain, we can sort it by the variance in each column so that we can select only the columns with higher variance because those are the most informative ones. And this is a form of dimensionality reduction. The advantage of this method is that it's really simple and it's fast because it's O of n, but doesn't induce higher order interactions, just direct co-occurrence. And what I mean by higher order interaction is that words that will be similar in this model are similar because they are in the same context, but not because they are in similar context. And contexts that are similar because the words that appear in those are also similar. Another important model is latent semantic analysis. In this case, we have a target which is a specific word, and the context is a document ID. The weighting scheme is TF-IDF, so the term frequency, how many times that word occur in the document, times the inverse document frequency, how many documents contain that word. Other weighting schemes can be used, obviously, and we calculate the similarity between the vectors using a cosine similarity, but the most important part of latent semantic analysis is that dimensionality reduction that is induced using singular value decomposition. Let's try to describe SVD in a nutshell. The goal of SVD is to reconstruct a matrix W multiplying 3 other matrices, U, sigma, and V, and those matrices contain orthonormal bases for U and V, and singular values for sigma. And what we actually end up doing is we're going to approximate this reconstruction by the first high singular values. So we're going to select K, that's going to be the first K columns in U, the first K rows in V, and the K by K submatrix of sigma. And we can use the U matrix or U times sigma matrix as our target matrix, and we can use V transpose as our context matrix. There's some advantages to this method. In particular, the reduced dimension K can be interpreted as topics, latent topics that are common among different documents. And reducing the number of columns can unveil higher order interactions. One disadvantage is that it is static, so that it's difficult when you have new documents and new words and new topics to update it. Also, it's a one-time operation. They're not intermediate results, and moreover, it's a really heavy computation, in particular in terms of memory. A more lightweight computation can be done by random indexing. It is a locally sensitive hashing method, and it approximates the distance between 2 points. It works by generating a random matrix R and projecting the original matrix A into it to obtain a reduced matrix B. And the reduced space B preserves the Euclidean distance between the points in the original space up to a certain constant, and that's mathematically true because of the Johnson-Lindenstrauss lemma. And so in practice, how does this method work? You have some data set, and for every word in the corpus, you create a sparse random context vector that has values between -1, 0, and 1. Class. And the target vector, for instance, for the word beer, is the context vector of I of the words they occur with times their frequency. So if you look at the right, if I have I drink beer and you drink, this is a super simple method, and the advantage is that it's really fast and it's incremental. If you have a new document, you can just create new context vectors, new target vectors on the fly. The disadvantage is that in many intrinsic tasks it doesn't perform as well as other methods, and there's some stochasticity in the process that can lead to some random distortion. And finally, you could also have negative similarity scores, which are kind of difficult to interpret. Another interesting example here is explicit semantic analysis. In this case, the targets are specific words and the context is Wikipedia article. And the assumption here is that Wikipedia articles are explicit topics. And so you have potentially 5 million dimensional vector for each word, and you're weighting it with the FIDF of the occurrence of the words in these documents. And the similarity is computed by cosine. Interestingly, you can also do dimensionality reduction in a very simple way, for instance, discarding the Wikipedia articles that are too short or the ones with not enough inlinks. And so the nice thing about this method is that if you look at this example where you have the word mouse, you can see that the word mouse correlated with several concepts, both mouse as a rodent and also mouse in computing. But if you sum the vector of the word mouse and the vector of the word button, what you obtain is a vector that kind of disambiguates the meaning of mouse, because now mouse in the computing meaning has a much higher weight than before. What's the advantage of this method? Well, first of all, it's really simple, and again, it's really fast, and it's interpretable. The dimensions have a meaning, which is super valuable. The disadvantage is that the assumption that Wikipedia pages are topics doesn't really hold. Also, it doesn't perform as well as other methods. And finally, the vectors are highly dimensional, although they're really sparse, so you can find ways to manage them. Another method is jobbing text. In this method, they introduce this notion of holding operation, which basically means remove some element from the input context to make it the target. And if you apply to a tuple, you obtain targets and context, and you can obtain vectors for those targets and context by their co-occurrence. The weighting scheme that they use is actually a custom measure that is similar to LIN, and the similarity, they use the lexicographer mutual information as a way to compute the similarity. So let's look at the example. Actually, I prefer the second one. Let's look at the second one where I have tuples that are windows of words within a document. And so, for instance, we can have tuples like I gave a book to, a book to the, and book to the girl. And if we apply the holding operation, we obtain target I and context whole gave a book. And you can have target gave and context I whole a book, and so on up until the end. And so you have all these contexts and all these targets, and you can compute your matrix. The advantage of this method is that it's really a generic processing operation, this holding operation, and deals with many context representations of different types of data, and deals with complex context, so you can have several steps in the tree, for instance, as context. The disadvantage is that there's no dimensionality reduction explicitly defined. There's no uncovering of hierarchical relations, and the implementation that it has, it's in MapReduce, and it's effective and fast only on clusters. Probably you're already familiar with Word2Vec, but I wanted to put it in the context of this target and context definition. And we're going to look at skip gramming and negative sampling, which is a slight variant of Word2Vec, where you have the target, which is a specific word, and the context is the window of n words around it. And the goal is to predict this window from the specific word, and the vectors are obtained by training the model to predict the context given the target. The error of the prediction is backpropagated, and the vectors are updated accordingly. And so basically you have an input representation can be seen as a one-hot representation with only the target word on. You multiply by a matrix of target vectors, you have a latent representation, and then you multiply by a matrix of context vectors to obtain an output distribution over the words in the context. And so if the predicted words are different from the actual words that appeared in the context, there's an error, and the error can be backpropagated to update target vectors and context vectors. In reality, that final softmax is really expensive to compute, and what we end up doing is we end up using negative sampling. We figure out a fake false context, and we try to predict pairs of target words and context words that actually appear in a true context to be 1, and the fake context words appearing with the target word to be 0. In the end, what you have is the log of the sigmoid of target and context words plus sum over the number of negatives of the expectation given words, k-words sampled from the distribution of the words, of the log of the negative of the product of the word vectors of the negative sample times the context vector. An interesting finding is that if we multiply the target vectors and the context vectors, what you end up having is a matrix that is the pointwise mutual information matrix minus a log of a constant, and this was figured out by Levy and Goldberg in 2014. So this connects matrix factorization methods with word-to-back. What is the advantage of word-to-back? It's an iterative way of factorizing a matrix, and it's relatively fast. It has several parameters that you can tune to improve the performance, and the default parameters can go a long way. They work really well. The disadvantage is that it has an inflexible definition of context. It doesn't use the dataset statistics in a smart way, and the columns are hard to interpret as topics. When word2vec was released, it was not compared with distributional semantic models at all, and so the distributional semantic models community tried to figure out if it actually worked better than the classic distributional semantic models or not. And the results were kind of interesting because some researchers said that yes, they work better, but when you use vanilla parameters. Some other researchers figured out that no, when you use optimal parameters for your distributional semantic models, word2vec doesn't work better than those. And other researchers figured out that if you trained on a really big corpus, that's actually where word2vec and in general neural word embeddings can work better than distributional semantic models. Another model along these lines is GloVe, where you have an explicit factorization of target times context matrix, which precomputes that matrix, unlike word2vec, and uses directly the statistics of the dataset, the frequencies of the co-occurrences. And so if you look at the loss here, what you end up having is you sum over all the words a function of the weights themselves, and then you multiply the target and the context word, and you remove the log constant value, and that is similar to what happens in word2vec. The advantage of doing this is that you use better the statistics of the dataset, so the method is actually faster than word2vec and converges to good solution with less data and much faster. Simple to apply to different contexts. The disadvantage is that in recent comparisons, it doesn't seem like it works as well as LSA or word2vec. Now let's talk about self-supervised learning and how it correlates with all these things that we discussed. We have seen how to represent words, but not how to represent sentences. And sentences are super important because that's how we communicate. And so we can't use the co-occurrence of sentences to obtain representations because those co-occurrences are extremely sparse. We should represent the meaning of sentences by combining word representations. The meaning of an utterance is a function of the meaning of its parts and their composition rules. This is a quote from Gottlob Frege from 1892. And so what could be these composition operators? There could be several ones. A simple one is just sum. So you could basically sum all the vectors of the words in a sentence to obtain a vector of a sentence. There could be other operators that have been studied by Mitchell and Lapata. The problem with these operations is that they are all commutative, and empirically they showed that it's really hard to perform better than just a simple sum. But the sum has one big problem. It's commutative, and so doesn't consider the word order. And so a trend of the mid-2010 is, well, let's learn how to compose words. And you could use a recursive matrix vector network, or a recursive neural tensor network, or for instance, a recurrent neural network to compose the words. And I guess now people that are familiar with deep learning are all familiar with, in particular with the recurrent neural network, where you have a set of vectors as input and the neural network encodes them, looking at one of them at a time in a sequence. The problem is that by doing that, what you end up having is a representation, but you don't know how to train it. In these works, they were using supervision for training these representations, but what people discovered is that you could actually train these representations in a self-supervised way, and they can be used across different tasks. So, for instance, when you do language modeling, you can interpret language modeling in terms of structuralism and distributional semantics if you consider that the words preceding a specific word in a sentence, for instance S1 to Si-1, are all the context, and the word Si is the target word. And so what you end up having is, given the context, which is the previous words, predict me the next word as a target. And GPT-2 is an example of this, for instance. But another way to use structuralist concepts is in bidirectional language modeling, where you use a word as a target and all the words on the left and all the words on the right of that word to be the context. An example of that is Elmo, where you have all context words as input, two LSTM layers of two different LSTMs, one that goes left to right and one that goes right to left, and then all the words are again outputs. So this is kind of tries to reconstruct the initial sentence. Another option that have been proposed is use masked language modeling, and the first method to use this masked language modeling was BERT. And so, for instance, BERT defines some masks and makes it so that words that are masked become targets and all the remaining words are context. So, for instance, we have a same sentence and we sample one time and we have quick jumps over as target and all the other words as context. We sample another time and we have brown fox over as target. We sample another time and we have brown fox over as target and the quick jumps, the lazy dog is context, and so on and so on. And on the modeling side, what BERT does is it applies masks to the input so that we receive only the context words as inputs, and applies inverse masking to the target so that we try to predict only the words that were masked in the input. The same principles and same ideas are also used for obtaining embeddings for graphs. So if you have a graph that looks like this, you can obtain the representation of each node, interpreting it as a target, could be its neighborhood of, for instance, distance 1 or distance 2. There's many papers that use this idea, for instance, DeepWalk or Notoback, but also GraphSage, that is a method that actually is used for supervised tasks, exploits neighborhoods for obtaining representations of nodes. And there's also many papers in the knowledge graph literature that use similar ideas. After the success of self-supervised learning in NLP, also the computer vision community started to catch up, and the examples of self-supervision in computer vision are really structuralist. One example of this could be in painting, where you have the context, which is an image, and the target is a part of the image that was carved out from the input. This is really similar to the masking that happens in BERT, for instance. Another example could be what you do in the denoising autoencoders, where your context is an image and you apply some noise on it and you try to reconstruct the original image without the noise. And you can see the noise as a kind of soft mask. A similar concept can also be applied in reinforcement learning, in particular when you want to have a model of the environment. And what happens is that if you have a sequence of states and actions, Z and A in this scheme, you can predict the state the next moment in time. And by predicting that state, it means that you have to learn something about the dynamics of the world that you're interacting with. And an example of that is this world models from Hai Schmid-Huber that was based on a previous idea from Schmid-Huber from 1989. And there's an example video here of a model that is hallucinating what will happen if it would strife left and right in Doom. As you can imagine, a really similar concept can be used to videos in general, trying to predict the next frame or some properties of the next frame. And it has been used for tracking moving objects, also for frame order validation, and finally, video colorization. Let's conclude here. So, What are the points that I wanted you to get from this? First of all, the structuralism can be a unifying interpretation for why many machine learning algorithms work. Many aspects of reality can be modeled in terms of targets and contexts, and context is king because the meaning of targets is defined based on the context. And finally, this is the most controversial statement in this whole presentation, is that self-supervised learning is just applied structuralism. This concludes this presentation, and I wanted to thank a bunch of people that influenced this talk in a way or another, in particular Magnus Algren, Alfio Agliozzo, Marco Baroni, Alessandro Lenci, Jof Goldberg, Andre Freitas, Pierpaolo Basile, Aurelie Herbelot, and Arianna Betti. Thank you for your attention.